Energy is always conserved. That is one of the three great conservation laws of physics. Conservation of energy, momentum, and angular momentum. Three quantities that are never created or destroyed. Although energy may change forms, the total amount of energy in the universe is constant. Energy. And more energy. No matter how, or how often it's used, regular or unleaded, energy is always conserved. But if that's a fact, and the law of the conservation of energy says it is, why isn't there always enough energy at hand? Every object in motion has a form of energy. But if energy is always conserved, how do moving objects ever get started? And once running, whatever direction they're moving in, if energy is always conserved, how can they ever stop? Some people work with more and more weight. Others try to work off some of the weight they walked in with. Yet even here, the vital question is, if energy is always conserved, why do muscles get tired? And why do weights fall? The answer, like exercise in general, has to do with work. In fact, part of the answer is work. And in exercising the conservation of energy, work has a precise definition. Work involves some force moving an object through the distance. Of course, the greater the weight, the more force required to lift it. And the greater the height, the more work. For all the work involved, its definition is easy. Work done in lifting equals force times height. When the work is being done near the surface of the earth, the force in this equation is the constant force of gravity, which equals mass times the acceleration of gravity. So, work equals mass times g times height. Sometimes, force makes mass accelerate, but here, force is used to overcome gravity, to lift the weight to a certain height. In the conservation of energy, the role of work is to transfer energy from one place to another. From muscles into steel, for example. The barbell has energy because of its height. That's potential energy, which is given the symbol U. In a constant gravity field, the potential energy of any object is written as mgh. In other words, its potential energy is exactly equal to the work that was put into it. It's called potential energy because, at any given height, it's ready to go into action. The greater the height, the more potential energy stored in the weight. Potential energy that can change into energy of motion. And potential energy which does change every time anything moves up or down. Potential energy by itself isn't conserved. In the law of the conservation of energy, then, what is actually conserved? Toward the end of the 16th century, Galileo Galilei asked himself a similar question. But it was one question for which even Galileo failed to find an answer. Nonetheless, while using inclined planes to slow down the acceleration of falling bodies, he did find something rather fascinating. No matter what path it followed, the ball would return to its original height, almost as if the ball remembered its original position. Of course, Galileo knew that an inanimate object couldn't remember where it had been. But he realized the ball retained something very powerful. If not memory, he wondered, what did the ball conserve? The answer didn't come speedily, but speed is the key to the answer. Starting from the same height, no matter what the slope of the incline, when the ball gets to the bottom, it's always going at the same speed. The energy of the ball's original height is still rolling along, transformed into speed. Human movement beautifully demonstrates how energy can change forms. Pushing a swing may not seem like work, but it is. And it increases the swinging girl's speed at the bottom of the arc and her potential energy at the top. So, while the flow of energy from one form to another may be child's play, it all begins with a little work. If work is done against a constant opposing force, as in lifting a block from one height to another, the work is the difference between the potential energy at the two heights. That is, the change in potential energy. If work is done with no opposing force, the work is the change in the quantity, 1/2 mv squared. This is a new kind of energy, an energy of motion. It's called kinetic energy. These athletes work their bodies up to maximum speed and then use that kinetic energy to launch themselves across amazing distances. Of course, when they do that, they lose the kinetic energy they've worked so hard to build up. But if there are only two forms of energy, potential and kinetic, and neither is conserved, how can any form of energy be conserved? There's a simple yet powerful explanation, but it takes a little leap of imagination. Potential energy changes constantly, and kinetic energy is in a constant state of flux. But when the sum of kinetic and potential energy is considered together, the totality of energy is a constant. In other words, energy, E, equals potential, U, plus kinetic, K, and that's a constant. Turning speed into height can be both a spectacular feat of coordination and an impressive demonstration of the relationship between kinetic and potential energy. In this case, the faster the run, the higher the vault. Muscles increase kinetic energy more and more, eventually to the limit of the athlete's ability. The pole changes all that kinetic energy into great potential. Suddenly, falling faster and faster, his accumulated potential energy changes back into kinetic energy. But something's wrong here. Now he has neither potential nor kinetic energy. And if energy is conserved, where did it go? There must be something else to be discovered. Not unlike any new world, the continent of physics was, and still is, ripe for discovery. The frontiers are rigorous. The discoveries, sometimes shocking. And often very controversial. But throughout the land of physics, the rewards can be greater than the hardships. James Prescott Joule gets credit for discovering the law of the conservation of energy. The son of a British brewer, Joule studied the efficiency of steam in electric engines for the family business. He devised an ingenious method of measuring how much mechanical energy turns into heat. A large weight, lifted to a certain height, has a precise potential energy, mgh. Joule arranged to have falling weights turn paddle wheels inside a carefully insulated container of water. Then he measured the water's temperature. In this way, Joule showed that a given loss of potential energy always turns into precisely the same amount of heat. That's because although it takes many forms, energy is always conserved. Whether it's in the form of potential energy, U, the result of doing work, W, or changing to kinetic energy, K. Or dissipating into yet another form, heat, or Q. All energy is conserved, strictly and absolutely. Only two forms of energy are mechanical, potential and kinetic. Work, force times distance, transforms energy, such as energy hidden in the biosphere, into the visible potential energy of the weight, poised high above the floor. Energy changes constantly, from potential to kinetic, from kinetic to potential, and back again and again, in countless ways. In whatever form, however, mechanical energy eventually begins to vanish once again, begins to disappear from sight and sound, not lost or destroyed, but transformed back into heat. According to the law of the conservation of energy, although energy changes forms, the total amount of energy in the universe is always constant.